Hello and welcome. In today's lecture, we're going to be talking about countability and density of sets of real numbers. These are two distinct topics, but I think they go well together. Before we can define either of these notions at the top, we have to go through a couple of preliminary definitions. So let's start with the definition of a one-to-one function. We say that a function f from a set S to a set T is one-to-one if distinct inputs in S give you distinct outputs in T. Such a function is also called injective. Imagine we have our set S pictured like this and our set T. F takes us from the left to the right. If it's the case that no two inputs get mapped to the same place, we would call this an injective or one-to-one map. If, on the other hand, there is a pair of inputs which get mapped to the same place, then this would not be one-to-one. Visually, that's what's going on, but let's look at a couple examples. Suppose f is a map from R to R given by f of x equals 4x plus 10. Is this map an injection? To determine if this map is one-to-one, it's actually best to think about what the outputs look like. So suppose that f of s1 equals f of s2. Okay, if that happens, then that means that 4s1 plus 10 equals 4s2 plus 10. But then we can subtract 10 from each side and we get 4s1 equals 4s2. Divide by 4, we get s1 equals s2. Therefore, the outputs are the same if and only if the inputs are the same, which means that this map is one-to-one. On the other hand, let's look at a different example. The function f of x equals x squared is not one-to-one, since, say, f of 2 equals 4, but f of negative 2 is also 4. In other words, distinct inputs are giving you the same output. Okay, now let's move on to our next definition. We say a function f is onto if it can reach all elements in the target space. So here we're assuming f is a map from some set S to another set T, could be the same as S, but it could be different. And when we write this kind of notation, what we're assuming is that we can plug in every element from S. So f is defined on all of S. However, it's not necessarily the case that f reaches all of T. If, for any element in T, there's an input which will send you to that element, then we say that f is onto. Another word for this is surjective. So onto and surjective are synonyms. Let's look at a couple examples here, and you'll notice it's key how we specify T. So for our first example, consider f sending R to R given by f of x equals 2x plus 5. If I choose any possible real number, so choose a possible output, let me call it y for obvious reasons, I would like to find an x which will map you to y. So we can say that y equals 2x plus 5 if and only if y minus 5 divided by 2 equals x. In other words, f of y minus 5 divided by 2 will send you to your choice of y. So this is an onto function because it's possible to get to all possible outputs y. Okay, so if I want to map to 10, I can do that. I just have to plug in 2.5. If I want to map to negative 500, I can do that. I just have to plug in the right input. So there's a way to reach all possible outputs. Let's look at f of x equals x squared again, and first let's treat it as a map from R to R. If I think of this as going from real numbers to real numbers, then this is not an onto function. And the reason why is pretty clear. There is no value of x in R satisfying f of x equals negative 10. I can't reach the output negative 10, so this would not be an onto function. There's no input which sends me to that output. On the other hand, if I restrict the way I write my function, so if I take this function and view it now as a map from R to non-negative real numbers, which you can denote like that, then this one actually is onto it, is surjective. And that's because there's a way to get to any non-negative number by taking the square root. Right? So if I want to reach 7.5, I would just plug in the square root of 7.5 or negative the square root of 7.5. I actually have a couple choices there. So this would be an onto map. Our final preliminary definition ties these two notions together. If a function s going from a set S to a set T has both these properties, it's both one-to-one and onto, or in other words, it's both injective and surjective, then we call f a bijection between S and T. Copying my diagram over from before, f is one-to-one, so distinct inputs will send you to distinct outputs. But f is also onto, so if I take any other output, say this one in T, then there must be an element in S that maps to it. So we can think of a bijection as sending each distinct element in S to a distinct element in T, and vice versa. You can essentially invert and go backwards from T to S, because every element in T is going to get mapped backwards to a distinct element in S. Some examples would include, say, f of x equals 2x plus 1 from R to R. This map is both one-to-one and onto. It's a bijection. You could invert it. Another example would be f of x equals x squared from, say, 0 infinity to 0 infinity. This would not be a bijection from R to R. It wouldn't be onto in that case. If I tried to go from R to the set of actual outputs, it wouldn't be one-to-one. But if I restrict S and T in this way, then it is a bijection. We would be looking at just this part of the parabola. Just this part of our function is one-to-one. You can actually describe that as passing like a horizontal line test. So every output gets sent to exactly one input. And we also cover the entire target space from 0 to infinity. So this would be a bijection from the set of non-negative numbers back to the set of non-negative numbers. What we're most interested in this lecture is using bijection to measure the size of sets, and in particular to compare the size of sets. The number of elements in a set is called its cardinality. We say that two sets A and B have the same cardinality if you can write down a bijection that takes you from one to the other. In other words, it's like every element in A gets paired up with exactly one element in B and vice versa. So that's this notion of having a bijection, and we can abbreviate that by just saying A is in bijection with B. Okay, so here we have 4 examples of sets A and B which have the same cardinality. What we're going to do is write down a bijection for each pairing. I'm not going to prove that each map we write down is actually a bijection, but you can work through that on your own. Okay, this first example, set A has 3 elements, set B has 3 elements. So I don't really need a bijection to tell you that these two sets have the same cardinality. But what would a bijection look like? Well, it could be something like f of n equals n plus 3. What this bijection is doing is taking 0, 1, and 2. It's sending 0 to 3, 1 to 4, and 2 to 5. So this is a bijection confirming that these two sets have the same cardinality. For our next pairing, we have 2 sets which each have 5 elements, so of course by visual inspection I can tell you that these two sets have the same cardinality. But let's write down a bijection. How about f of n equals 1 over n? That will take 1 to 1, 2 to a half, 3 to a third, 4 to a fourth, and 5 to a fifth. Notice here it doesn't have to preserve the order with which I wrote these sets or anything like that. All it has to do is give me a map from each and every element in one set to the other one in such a way which is one-to-one and onto. Okay, the next example is a little bit trickier because here the sets have an infinite number of elements in them, so we can't just look at them and count. Our set A is the set of all real numbers, so this is the whole number line. And B, you might look at B and think, oh, it's only half as big because B is the set of positive numbers. But actually, these two sets have the same cardinality, so this might be the first result which is surprising. The set of real numbers has the same number of elements as the set of just positive numbers. Okay, that might be surprising, but here you have to trust your bijection. So let me write down an actual bijection. We're going to say f of x equals e to the x, the exponential function. We haven't looked at this function in much detail, although we will a little later, but the graph of e to the x has this behavior. It passes a horizontal line test, meaning that it's one-to-one. So if I pick any positive output, there is exactly one input which gets mapped there. And because I can do that for any positive output, it's also onto. So this is a bijection from the set of all real numbers to the set of positive numbers. So what this bijection does is give us a way to pair up every element in A with exactly one element in B and vice versa. So we can write down a pairing, and our pairing is going to look kind of like if I take 0 in A, that pairs up with e to the 0, which is 1, in B. If I take negative 10 in A, that pairs up with e to the negative 10 in B. If I take natural log of 2 in A, that pairs up with e to the natural log of 2, which is just 2, in B. So these two sets kind of go hand in hand. So these two infinite sets, in fact, have the same cardinality. Our last example are two infinite sets again because there are infinitely many elements in A. A is the closed interval from 0 to pi over 2. And there are infinitely many elements in B. B is the closed interval from 0 to 1. Again, I'm just going to write down a bijection. Let's have f of x equals sine of x. Sine of 0 is 0. Sine of pi over 2 is 1. And just as a map between these two sets, sine of x is a bijection. Sine of x in general is not one-to-one. It oscillates. If I thought of B as all real numbers, it wouldn't be onto, right? So sine here is working because of my choice of A and B. This is not the only bijection you could write down. It's not unique. It's just one possible choice. For each of the examples we just did, I could actually write down a nice closed form function f. However, you can't always do that, and you shouldn't even really want to. We want to be flexible with our notion of a bijection. So if I say that there's a bijection between two sets, I don't need to make precise exactly what the recipe is. I just have to know that there's a way to pair up the elements. So for example, if my set A consisted of pi, e, and negative 10, and my set B consisted of 0, 1, and 2, I would really struggle to write down a nice function that mapped you from A to B. It is possible, but it would not be nice and pleasant looking. But if I just need to say that these two sets have the same number of elements, I can actually say, well, there's a bijection. Just send pi to 0, e to 1, and negative 10 to 2. That gives me a mapping from A to B, which is one-to-one and onto. As we just saw in our previous 4 examples, the finite cases were not very interesting. If I know each set has 3 elements because I can count them, then there's no real need to write down a bijection in order to convince ourselves that the two sets have the same cardinality. The infinite case, though, is much more interesting. So what we're going to do next is look at sets which have an infinite number of elements in them, and yet we'll be able to say that certain sets have different sizes. So somehow we'll make precise the notion that you can have two sets which individually each have an infinite number of elements, and yet one of those sets is much, much bigger. So this is just a quick look at the nature of infinity. There are different ways to say that you have an infinite number of objects. So in particular, when we're talking about subsets of real numbers, we are interested in two cases. If it's possible for us to take an infinite set A and establish a bijection with the natural numbers, then we're going to call A countable. As a quick remark, the word countable can also mean finite. So here we're talking about countably infinite. So if I say the word countable, what I usually mean is it's a countably infinite set which can be put in bijection with a set of natural numbers. If a set has just 3 elements in it, some people might call that countable, but I would make precise that it's finite. Okay, we already know that there's at least one set out there which is countable because the set of natural numbers is an infinite set in its own right, and it's in bijection with itself via f of n equals n. So that's an example of a countably infinite set. What you might not yet be able to picture is the second notion. If A is an infinite set which cannot be put in bijection with a set of natural numbers, then we say that A is uncountable. These two definitions give us fundamental differences between countable and uncountable sets. So in particular, if a set is countable, then I can say that there's some bijection between counting numbers, 1, 2, 3, 4, and on, and the set A, which it now makes sense to list out as A sub 1, A sub 2, A sub 3, A sub 4, where this list I'm creating is based off of having a bijection sending us from N to A. So this is my set N, and A is some unknown, I'm not making precise here what A is, it's just an infinite set, and I can say that there's some way to map from counting numbers to A in a manner which is both one-to-one and onto. Such a set is also called denumerable. The idea is that we can enumerate the elements of A, we can list them out. Being able to say 1, 2, 3, 4, map to A like this, A1, A2, A3, A4, means that I can actually sit in a rocking chair on a porch and spend the rest of my life listing out the elements of A. I'll never finish because A is infinite, but there's an ordering. I can order the elements of A just like I can order the natural numbers. A doesn't have to be an ordered set in its own right, but there's a manner in which you can list out the elements of A. So we say A is denumerable. On the other hand, if you're looking at an infinite set which is uncountable, then you cannot even begin to list out the elements in any kind of meaningful way. So I couldn't sit in a rocking chair for the rest of my life and have any sort of clever approach to stringing out the elements in an uncountable set. Because if I could say, well, the first element is this, the second element is that, the third element is such and such, then that itself would be a bijection with the natural numbers. So this notion of an uncountable set means you can't even list them out. You could not begin to denumerate them in any way which would ever touch every element in A. So we cannot list these out. We can't enumerate them because the ability to enumerate them, the ability to write them down in an infinite list, is equivalent to having the ability to put them in bijection with the natural numbers. So these are fundamentally different types of infinite sets. Okay, let's look at a few examples. Each of the examples we have here is a countable set. So what I'm going to do to convince you that each of these sets is countable is give you a bijection from the set of natural numbers to the given set. So for our first example, consider the set of non-negative integers. Well, that's like the natural numbers together with 0. So sometimes students say, no, these don't have the same cardinality because the one on the right has one more element. It has all of the elements of the natural numbers plus 1. And I understand the objection, however, that's just not how an infinite set works. We have infinitely many elements in the set of natural numbers, we have infinitely many elements in the set of non-negative integers, I can't really say that this is the same infinity as on the left, but plus 1. I know it's tempting, but that's just not how it works. Whenever you don't like that notion, fall back on a bijection. So here's a bijection. Let's let f of n equal n minus 1. Now what happens if I start plugging in natural numbers? Well, 1 goes to 0, 2 goes to 1, 3 goes to 2, etc., etc. This gives me a way to pair up each and every natural number with exactly one non-negative integer and vice versa. So this is a bijection between these two sets. We can exactly pair up their elements, so they must have exactly the same size. Similarly upsetting for students at first glance is the fact that the set of natural numbers has the same number of elements as just the set of even natural numbers. I made the same objection when I was first learning this material. I said, no, the set on the right has half as many. Therefore, they can't have the same cardinality because this is missing numbers from the left. I completely understand why someone might think that because, of course, I felt the same when I first learned it, but we can write down a bijection between these two sets. If we let f of n equal 2n, then if I plug in the natural numbers, 1, 2, 3, 4, I'm going to get mapped to 2, 4, 6, 8. So this is an onto function. It's also one-to-one. So this is a bijection from the set of natural numbers to the set of even natural numbers. Lastly, the set of natural numbers is also in bijection with the set of all integers. Again, you might feel like there are more integers than natural numbers, but that's not what these infinite cardinalities actually tell you. Here my bijection is going to be piecewise defined. Again, that's why I wanted to point out that you don't want to get too attached to having an actual explicit bijection. I can give you an explicit bijection here. First, if we have an odd natural number, subtract 1 and divide by 2. If we have an even natural number, negate it and divide by 2. Okay, so I had to spend some time to come up with this. It wasn't totally obvious at first glance how to do it, but the idea is let's kind of divide and conquer. So here my odd natural numbers are going to get mapped to all positive integers, and also 0, I believe, is in this case. My even natural numbers are going to get mapped to all negative integers. So it's kind of like I'm splitting my natural numbers, sending half to the positive integers and 0, and half to the negative integers. If you don't yet see what's happening, let's write this out. So our natural numbers are going to look like 1, 2, 3, 4, 5, 6, etc. Let's see what f of n looks like. If I plug in f of 1, 1 is an odd number. 1 minus 1 divided by 2 is 0 divided by 2. So that's 0. 1 gets sent to 0. 2 gets sent to negative 2 divided by 2. That's going to be negative 1. 3 is going to get sent to 3 minus 1 divided by 2. So that's 2 over 2 is 1. 4 gets sent to negative 4 halves. That's negative 2. 5 gets sent to 5 minus 1 is 4 divided by 2 is 2. 6 is negative 3. Okay, so notice that the set of all integers, z, is not a set which has a beginning and an ending in an ascending order. I can't say this is the smallest integer and from here we keep going like we can with the natural numbers, right? So you can't order z with a first element which is biggest or smallest. This just doesn't work that way. However, what this bijection is doing is giving us a way to enumerate or list out all of the elements in the set of integers in a way which will eventually cover every integer. So this is that ability to enumerate the elements I was trying to describe on the previous slide. So of course 0 is not the biggest or smallest integer, but if we keep following this pattern, 0, negative 1, 1, negative 2, 2, negative 3, 3, negative 4, 4, we would eventually cover every integer. You may have thought that the previous examples all felt sort of similar. Each of the three examples was kind of like the natural numbers with a slight difference. The first one we added in 0, the second one we looked at only even natural numbers, and then the third one we looked at the set of all integers, which is like positive natural numbers, negated natural numbers, and then also 0. The fact that all three of those end up feeling the same tells you that maybe some theorems can be stated here. In the first theorem, we say that if T is a countably infinite set, and it has an infinite subset, then that infinite subset itself is also countable. This theorem would have told us that our second example, the set of even natural numbers, was a countably infinite set because the set of even natural numbers is an infinite subset of natural numbers. So we could have concluded that that was countable had we known this theorem. Okay, we won't prove this. You can think over how you would demonstrate it. Let's look at the second theorem. This has two statements. If I have a finite collection of countable sets, so suppose A1, A2 through AM, where M is a finite number, each of these sets is a countable set in its own right. If I put them together, their union is countable. As a remark here, because we're going to use this notation in the proof, since each one is countable, then that means that I can denumerate each one. So suppose that I'm looking at A sub k. If this is a countable set, then it can be put in bijection with the natural numbers so we can list out its elements. I'm going to call each element little a sub k to show that it comes from the set big A sub k, but then I'm going to append a subscript 1 showing that this is like the first element. This is where we might map natural number 1. A sub k2 is where we would map natural number 2, A sub k3, and on and on. Okay, we'll use this notation in a minute. The second statement in this theorem, which we won't prove, is that if you actually have an infinite collection of countable sets, so you have A1, A2, A3, A50, A5000, etc., and each one of those is countable, then their union is countable. So countable union of countable sets is itself a countable set. We will prove the first one, and our proof is going to rely on the fact that little m in this statement is a finite number. So you can't immediately take the same proof and use it to demonstrate the second statement. However, there is a way to adapt this proof for the second statement. If you're interested, we can talk about it in the forum. But let's just focus on the first one. What we're going to do for this first statement is we're going to describe how the bijection works. So I'm not going to write down a closed form expression like f of little n equals such and such. I'm just going to say how you would make a bijection, a mapping from natural numbers to this collection of countable sets. Okay, so what we're going to do is send natural numbers to these sets in a way that divides and conquers again. So I'm going to send the natural numbers 1, m plus 1, 2m plus 1, 3m plus 1, 4m plus 1, numbers of that form, to the first set A sub 1, which we can denote as A sub 1, 1, A sub 1, 2, A sub 1, 3, and on. So the pattern here is really like 0m plus 1, 1m plus 1, 2m plus 1. Then we're going to send natural number 2, m plus 2, 2m plus 2, 3m plus 2, 4m plus 2, etc., to the set A2, which looks like A21, A22, A23, on and on. And we continue in this form. So we would send 3m plus 3, 2m plus 3 to the members of A3 until we get all the way to number m, the natural number m. So that's like 0m plus m. Then we would do 1m plus m. So we're going to be sending m, 2m, 3m, 4m to A sub m, whose members look like AM1, AM2, AM3, on and on. I claim that this is a bijection. And at this point, we've essentially finished the proof because here's our bijection from the natural numbers to this collection of countable sets. Let's see what it looks like if I actually designate M as the number 3. So in other words, I want to show you that there's a bijection between the set of natural numbers and the sets A1, A2, A3, taken as a union. What we're going to do is map natural numbers forward. So let's list out the natural numbers. I think I'll do 1, 2, 3, 4, 5, 6, 7, 8, 9. I think that's enough to see it. Okay, so according to our proof, we should send 1, 3 plus 1, 6 plus 1 to A11, A12, A13. So that's like 1 goes to A11, 4 goes to A12, 7 goes to A13, then 10 would go to A14. Next we're going to send 2, 3 plus 2, and 6 plus 2 to A21, A22, A23, etc., etc. So then 11 would go to A24. Lastly, we send 3, 6, 9, 12, 15 to A31, A32, A33, on and on. So 3 goes to A31, 6 goes to A32, 9 goes to A33, and we would continue across the natural numbers in this way. So here I don't have a formula for this bijection, I have a description for it. And, is it really a bijection? Well, is it onto? Will we eventually get to A3, 11, the 11th member of the set A3? Yes, we will. Eventually we'll get there. And is it one-to-one? Do multiple natural numbers map to A22? No, by construction. So this is a bijection between the set of natural numbers and the union of these sets A1, A2, and A3. We could have used this theorem to establish that the set of integers is a countable set, because with the set of integers we're taking the union of non-negative integers, which we already showed in the first example was a countable set, together with negative natural numbers, or just all the natural numbers with a negative sign in front. We could view that as the union of two sets, and then we would see via this theorem that the set of integers really was countable without needing to write down that piecewise defined bijection we did a minute ago. Our next result is that the set of rational numbers is countable. In other words, the set of all numbers which can be written as a ratio of an integer over an integer is a countable set. Now this set I think is much more surprising because for one thing there is no smallest rational number. Just start with the rational number 1, divide it by 2, divide it by 2, divide it by 2. You can do that forever and you're always going to generate more rational numbers just between the numbers 0 and 1. So we have infinitely many rational numbers between 0 and 1, infinitely many rational numbers between 1 and 2, etc. But we're saying that they're actually the same amount of rational numbers as counting numbers. I found this result really surprising when I first learned it. Okay, our proof is actually going to be pretty short. We're going to show that the set of positive rational numbers is countable. And then we'll use that previous theorem to put that together with the set of negative rational numbers together with 0 to conclude that overall the set of rational numbers is countable. This proof is fairly short because we're going to rely on a bijection which is actually not too hard to describe. So first, take all rational numbers and write them in reduced form. Don't write 2/4 or something like that, write 1/2. Once all of our rational numbers are written in reduced form P over Q, generate these sets A sub n, defined to be the set of all rational numbers whose reduced form is P over Q, in such a way that the sum of P and Q is n. Okay, it's going to be helpful to write down what the first few of these sets looks like. A sub 1 would be the set of all P over Q such that P plus Q equals 1. Since we're just looking at positive rational numbers here, we can't find any such elements, right? 1 over 1 would give you 1 plus 1 equals 2. So you could do 0 over 1, but that would be the 0 element. So this is actually the empty set. A sub 2 is going to be 1 over 1 and no other rational number. A sub 3 will be 1 over 2 and 2 over 1. Those are the only rational numbers which, when written in reduced form this way, have a numerator and denominator which sum to 3. A sub 4 would be 1 over 3. You could try to then do 2 over 2, but that's not the reduced form of that number, so we'll cross it out. And then 3 over 1. A sub 5 would be 1 over 4, 2 over 3, 3 over 2, and 4 over 1. A sub 6 would be 1 over 5. Let's see, not 2 over 4 because that's not reduced, not 3 over 3, not 4 over 2, then 5 over 1. Okay, I believe those are the only two elements in A sub 6. Okay, so starting with A2 really because A sub 1 was empty, A2 and onwards is actually going to give us a way to enumerate the rational numbers, and then because we can enumerate them, we can put them in bijection with the set of natural numbers. Okay, so what's our ordering or our enumeration for the set of positive rational numbers? What we're going to do is we're going to write down the elements in Q by listing out A1, A2, etc. Actually, by listing out A2, A3, A4, since A1 was empty. Okay, so I claim the set of rational numbers can now be enumerated as first all of the elements in A sub 2, that was actually just 1 over 1. All of the elements in A sub 3, that was 1 over 2, 2 over 1. All of the elements in A sub 4, that was 1 over 3, 3 over 1. All of the elements in A sub 5, that was actually a big one, so it was 1 over 4, 2 over 3, 3 over 2, 4 over 1. Then all of the elements in A sub 6, which was just 1 over 5 and 5 over 1, etc. This ability to enumerate the set of positive rational numbers then gives us a way to define a bijection. We will send the number 1 to the first element, the number 2 to the second element, the number 3 to the third element. And even though I don't have a way to write down a closed form expression, I don't have a formula for this bijection, it's still a bijection from the set of natural numbers to the set of positive rationals. If you want to confirm that it's a bijection, you first have to ask yourself, is it 1-to-1? And the answer is yes, because once you've put a rational number in reduced form, its sum is unique. The rational number 5/7 has a sum of 5 plus 7 equals 12. It will appear in A12 exactly once, and that's it. So each rational number only makes one appearance in this enumeration. So only one natural number will map to it. That's the condition of being 1-to-1. The second question is it onto or is it surjective? And again, because each reduced form has a sum, each rational number will make an appearance. So now that we've created a bijection from the set of natural numbers to the set of positive rational numbers, we conclude that the set of positive rational numbers is countable. Next, we say that since f of n equals negative n is also a bijection, taking us from the set of positive rational numbers to the set of negative rational numbers, the set of positive rationals and the set of negative rationals must have the same cardinality. That's not very surprising, right? It's clear how to pair up positive rationals with negative rationals. Take the union of those two sets together with the single element set 0. Since that's the union of two countable sets together with a finite set, that means that the set of all rational numbers must also be countable. Okay, so even though the set of rational numbers seems much bigger than the set of counting numbers, because between any two counting numbers you have infinitely many rational numbers. In fact, they're the same size. You can create a pairing between each counting number and a rational number. Therefore, these two infinite sets have the same size, so it makes sense to say the set of rational numbers is countable. For me, that was a surprising result when I first learned it. And at this point, every set we've investigated in the last few minutes has been countable. So you might think, well, maybe there's really just one way to have infinitely many objects. Maybe every set, which is infinite, is countable. So every set has an enumeration. You can list out the elements. In fact, that is not the case. Our next result is a famous result from the mathematician Cantor. This is a 19th century result. Cantor was really interested in the structure of real numbers, and he came up with a lot of these kind of challenging notions that were not easily embraced by his contemporaries. So we're going to show now that the open interval, consisting of all numbers between 0 and 1, is an uncountable set. This is a very famous proof. What we're going to do is basically an adaptation of what's called Cantor's diagonalization argument. It's called the diagonalization argument because we're essentially going to go down this main diagonal here and create a contradiction. So for the sake of contradiction, suppose that there exists a bijection taking us from the set of natural numbers to 0 to 1. If we had such a bijection, then we could enumerate all of the elements in the open interval from 0 to 1. So what this chart I've created here is trying to do is imagine such an enumeration. The natural number 1 must map to what you would think of as f of 1, and then that's going to be some decimal number between 0 and 1. Here I've imagined the first 6 digits of this number. So, imagine the decimal goes on, if it terminates early, the rest would be zeros. Otherwise, these digits could be, whatever they are. We'll denote the first 6 digits of this first number as A11, A12, A13 through A16. We've seen that kind of indexing earlier in this lecture. Likewise, the natural number 2 maps to something which we'll denote as A21 through A26, that being the first 6 digits. I'm just putting 6 digits here because we're going to illustrate how this proof works in a second. Okay, so we will continue in this way. Assuming that our set of numbers between 0 and 1 is countable gives us a way to list out the elements. And then what I've written out here is the list. So if we assume that there is a bijection, we can make such a chart. Now what I'm going to do is choose a number x, which by construction is going to live in the open interval between 0 and 1. And x is going to have the form that its first number is 2 if A11 is not equal to 2. Otherwise, it would be 3. Its second number will be 2 if A22 is not equal to 2. Otherwise, it will be 3. To see what this proof is doing, let me guess what the first 6 elements in this listing look like. So I'm going to just put down some decimal numbers between 0 and 1 to take the place of F1 through F6. So let's say the first one is 0.217753 ... Let's say the second number is just a half, so that would be like 0.500000. That's 5 digits, I need 6. ... Let's say the third number is 0.121544, etc., etc. Let's say the fourth number in our list is 551288. I tried to come up here with 6 fairly random looking numbers between 0 and 1, where I'm imagining that these are the first 6 numbers in my enumeration of the open interval between 0 and 1. Now we're going to follow this definition to write down what the element x must look like. Okay, so what is the first digit for x? B1. Well, what we're going to do is come to the first decimal digit in f of 1, figure out what it is. In this case, it's 2. And then come to our piecewise definition for each digit in x and figure out what the corresponding coordinate for x should be. Since a 1, 1 was 2, that means I need to come down to the second line here. The first digit in my decimal expansion for x must be 3. Okay, what about B2? For this, what we're going to do is come to the second number in the second decimal. That is not 2. Therefore, I make B2 2. In this case, I'm following the first line in the definition of this piecewise creation. Now for B3, we come to the third digit of the third number. That is the number 1, which is not equal to 2. Therefore, the third digit of x is 2. Again, that follows the first line. For B4, we come to the fourth digit. Now we're actually back to the scenario of having a 2. Since a 4, 4 equals 2, B4 must be 3. That's following the second line of this piecewise construction. For B5, we're interested in A5, 5. That's not equal to 2. Therefore, we make B5 2. And then lastly, for B6, we come to the sixth element of the sixth row in our chart. That is 2. Therefore, according to the second line in our piecewise construction, B6 should be 3. And we would continue in this way for every single digit of x. So x starts to look like 3, 2, 2, 3, 2, 3. That's why, again, it's the diagonalization argument, because we're going down this main diagonal here. Here's the catch. Because the first digit of x is different than the first digit of f of 1, x cannot be f of 1. The second digit of x is different from the second digit of f of 2, so x cannot be f of 2. In fact, x can't be f of n for every natural number n. That's by construction. That's how this piecewise construction was set up. It makes it so that x does not appear in this listing. Therefore, there can be no bijection from the set of natural numbers to the open interval from 0 to 1. Because here we're showing that you can leave somebody out. You're not going to be onto. Since f is not onto, it's not actually a bijection. So the open interval from 0 to 1 is an uncountable set. That means that you cannot list out those elements. There's no way to recite all of the numbers between 0 and 1 in any fashion that would ever touch every number. There's no sensible way to list out those numbers. Even if you can make your list infinite, any listing of those numbers will not include every possible number between 0 and 1. Let's look at some results which follow immediately from Cantor's diagonalization argument. Since the open interval from 0 to 1 is just a subset of R itself must be uncountable. But since we can also take R and say that R is the union of rational and irrational sets, and we've already shown that the set of rational numbers is countable, then the set of irrational numbers must be uncountable. That means that there are more irrational numbers than rational numbers. I think that's a neat result because sometimes I will ask students when I'm teaching this in the classroom, like, quick name a number, and people typically name rational numbers. Like if you just think of a random number, it's going to be 5 or a half or something like that. Sometimes people will say e or pi or square root of 2 or something like that, but we don't have a lot of names for these irrational numbers that aren't like 3 times the square root of 2. And yet there's so many more irrational numbers than rational numbers. I want to finish this lecture with a brief discussion of density. This is a property that both the set of rational numbers and the set of irrational numbers have in common. So although we just said that the set of rational numbers is countable and the set of irrational numbers is uncountable, so somehow it's much, much larger, both of these sets are what we call dense on the real number line. Here's what it means to say that the set of rational numbers is dense in R. If you have any two real numbers a less than b, there's a rational number r sitting between them. So how we picture this is we have our number line. Take any two numbers a less than b, you can find a rational number between them. And now you can see why the word density is going to be used here, because between A and R, we can find another rational number using the same property. Likewise, between R and B, we can find another rational number. And then between any pair of the numbers we now have labeled on the number line, we can find a rational number. So the idea is that we can continually zoom in on the number line and we're always going to see rational numbers. The set of irrational numbers is similar. So between any two real numbers x less than y, you can find an irrational number. And likewise, now between x and s, we can find an irrational number. Between s and y, we can find another irrational number. So as you zoom in on the number line, you're always going to be able to find irrational numbers. I think density here is neat because we just said that the set of irrational numbers is uncountable, and yet now we're saying that between any two irrational numbers is a rational number, and yet somehow there are far fewer rational numbers than irrational numbers. So when I was a student, I found that really challenging, that there are many, many more irrational numbers than rational numbers, and yet between any pair of irrational numbers, we can find a rational number. So I thought that was a really hard thing to picture. I still can't really picture it, but I accept these results. I hope you do too. I'll leave it there for this particular lecture. Thank you for your time.